Hi, we're going to get started now. Okay, so first off, a few things. I believe this class as a whole is ending October 1st. So just something to look out for. October 1st will be the last class, 2 days, September 24th. I believe October 1st is the last class anyways. If it's not October 1st, it's one of the classes next to it. So yeah, we'll talk more when we get there. Right. Hold on. Okay, so today we're going over functions. So radicals, I've explained this before. So first off, but I'll go more into detail. So let's graph a radical. So if you go graph one, it looks like, so first off, a radical and x squared is inverses of each other if x is limited to positive or non-negative. So as I've explained before in the inverse last class, an inverse function is the reflection of its original function across the y equals x function line. If I didn't explain it, I'll explain it now. But an inverse function is its original function reflected over the y equals x line. So what we do here is, again, reflected, and you see here it rises greatly at first before slowly coming to a pretty flat, or should I say more flat. It never really goes towards flatness or horizontal, but and more on radicals, but solving equations with radicals. So let's say we have something like this. So what do we do here? So we can't really square this to get rid of this side without screwing this side over, because it'll become a mess. But what we can do is multiply this by 2x plus 10 minus no, never mind on that part. We do square it actually. So after squaring, 3x, no, x plus 17 minus 2x plus 10 times 7 minus x equals 2x minus 2. Therefore, 15 minus x equals 2x plus 10, 7 minus x And if you square both sides, it'll turn into a quadratic, which you could easily solve. Supposedly the answer is x equals 3. If we plug that in, excuse me, this should be 19 since we add here. So if you put x as 3 into this equation, it works out. So just a general strategy, but to get rid of these radicals, whether they're 3 or 4 or 2, you should move said radicals to one side, or try to get rid of radicals by squaring or exponentiating. So 3x plus 4 equals x plus 3. You can triple this side by 3 in order to get rid of the radical. So like x squared plus 9 equals 2x minus 3. If you square this, it turns into a quadratic. Does anyone have any questions on that? If not, I'll move on. So absolute value. So I've mentioned this before, but first of all, this is what absolute value looks like. It's two lines with whatever's in between. But what absolute value essentially does is measure the distance between x, or the input, and 0. So if x is negative, then I shouldn't say negative x itself is negative, then the distance here is negative x because x is negative, so negative x is positive. And now if x is positive, then the distance is x, which is positive. Does anyone have any questions on that? So whatever absolute value, whatever is inputted into here is positive. So if we graphed it, normally a y equals x curve would look like this. But since this, whatever here has to become positive, then this gets reflected onto it, the x-axis, and becomes a sort of V. So let's try some things out. Not that. 2x minus 9 absolute value equals 5. So what are the values here that we need to get to 5 is what we should ask ourselves. And well, that's positive, negative 5, since plus 5 is 5, negative 5, absolute value 5. So 2x minus 9 equals 5, or 2x minus 9 equals negative 5. What you get from this is x equals 7, this x equals 2. So the solutions to this is 7, 2. Note that we have two different solutions, which may or may not be the case, whether or not the absolute value stretches here. But what if we had multiple of them? So first off, let's take that x is bigger than 3. So this would be positive, this would be positive. So we can here not slash out, I should say, 2x minus 1 equals 5. So x equals 3 is the solution, and you plug it in to check, and it works. What if x is less than 3, but bigger than -2? Well, now that x is less than 3, this is negative. So this needs to be flipped to become positive, and this stays the same. So these two cross out, and interesting enough, pretend that there's a equal sign here, but interesting enough, this means that anything between -2 and 5 and 3 is a solution. So put in anything -2, 3, it works. What about the last interval? This is very similar to our quadratic inequalities, where we find the interval based on what's the constant next to the x. So I hope it reminds you of something. So again, both sides are, this is negative, this is also negative. So -5 minus 2x equals 5. Sorry, not -5. This is -2, this is 3, so it's 1. So 2x equals -4, x equals -2, which is also part of this. So the solutions to this one are kind of boring, but I hope you see the point. So like x plus 3 plus 2 minus 5x. So let's take x is, so first off, let's take the intervals -3, and this is 2/5. So let's take x more than 2/5. So this is positive, this is negative. So also note that this is negative with a greater x because the coefficient of x here is negative. X plus 3 minus 2 plus 5x equals 7. X equals 1, which plugging it back in is a solution. So this is our solution, first solution. What about x more than 2/5, more than -3? Well, now that it's less than 2/5, this is positive. So 5 minus 4x equals 7. X equals -half. Check, plugging it back in. This is 5/2. 9/2. It is a solution. So -half is our second solution. X less than -3, which makes this negative and this positive. I'll erase this to give us some space. So 2 minus 3 minus 5x minus x equals 7. And now negative 6x equals 8. So x equals negative 4/3. However, that does not agree with our initial assumption that x is less than negative 3. So what we have here is a sort of bogus solution. So this is not a solution because it does not follow our initial restriction. Okay, so if you wanted to have two variables in here, how does this work? Well, it's again the same principle. So I'll draw something out, but for x more than negative 1, which is this line, and y2, which is this line, we have our interval. So if we take that both are positive, which is this quadrant, called unofficial quadrant, which is one that we've created, not something that was there before, x plus y equals 6, and we can graph that onto there. So I don't have intervals here, but I hope you get this sort of scale. So we can draw x plus y equals 6 only in our intervals. So what about this side? This side, both are negative, so we'll have x plus y equals negative 4, I believe. So it'll be something like this. Next, we have this end. So on this side, x is negative and y is positive. So we have y equals x plus 6, I think. No, that's not right. No, it's 8, since this becomes negative 2 minus 1, put this on the other side plus 3. So as you can see, these actually connect. And our last segment is this one, which is y equals x minus 2. So first off, these lines are, if you wanted to observe something, these are rectangle. This is a rectangle because these two lines are perpendicular and so forth. If you go more into geometry, you might see more absolute values graphs, but that's about it for here. So floor and ceiling. So what is floor and ceiling? Well, let's say we have x. This is floor x. This is rise or ceiling x. Sometimes people call this ceil x, though this is kind of more programming since you have to write it. I've seen this before, but but this could also mean a list of X, so it's kind of vague. I would recommend using these two symbols since they obviously show the floor and ceiling. But what a floor basically does is, let's say X is 4.5 to 4. It rounds a number down to rounds down a number to the nearest integer. Rounds down to the nearest integer that's less than X. So 4.7 and 4, 5.2, 5, pi, it does not have to be rational. 3, square root 2, 1, square root 5, 2. And for the last case, 4 becomes 4 since it rounds down to the nearest integer, which is 4. X is a sort of opposite where it rounds upwards. So 4.5, 5, 4.7, 5, 5.2, 6, pi, 4, square root 2, 2, square root 5, 3, and 4 is yet again 4, since 4 is the nearest integer to 4. Now notice that floor 4 is 4, ceiling 4 is 4. So square root X equals ceiling X. No, not like this. 1, X is an integer. So 1 X int. Another thing to a more obscure say function is the fractional part of X, which is 2 brackets. I'm not really drawing the brackets well, but what the fractional part of X is, what it seems like, it's the part of X after the ints. Its formal definition, which isn't something you should remember it by, but as a sort of last resort, is that X equals floor X plus fractional X, or that fractional X is X minus floor X. So 4.7 in its fractional part is when you cut off the integer part, so it's 0.7, 4.2, 0.2, pi, it's pi minus 3, since it's pi minus floor pi, which is 3. 7.6, 0.6. Also note that the fractional part of X is always less than 1, and always more than or equal to 0. Also, this is when X is not an integer. Isn't. So 4.7, 4, 4.75, 4 plus 1 is 5. You can clearly see the point, the reasoning behind this. Another thing I should address is negative numbers. So negative 5.7. So first off, what's the floor of this? Well, -5 is not the floor. -5 is actually bigger than negative 5.7. So the floor is -6. It's easy to get tricked by, so just be careful. Similarly, the ceiling is -5. As a sort of trick question, what is fractional x? One, or I should say, fractional negative 5.7. I'll be right back. I need to do something. All right, I'm back. Oh, I just went to the bathroom. So the fractional part of negative 5.7 well, one might say it's 0.7, which is, but if we take the formal definition of fractional x, it's negative 5.7 minus negative 6, which is 0.3. A good thing to note when doing fractional or floor negatives is that the fractional is always an integer interval away from the real thing. Okay, so let's move on. I'll go over one problem is this 2x. So we need to, so first off, x can be anything. We're finding a and b. So we can actually form this into a single fraction, x minus 2a plus b x minus 3. Note that the denominators are the same, so we can cross these out. So 2x equals x minus 2a plus b times x minus 3. So 2x equals x minus 2a plus b x minus 3. Since x can be anything, this has to equal 2x, which means that a plus b x equals 2x, while minus 2a equals minus 3b equals 0. So a plus b equals 2, 2a plus 3b equals 0, since I just reverse the sign so it's easier. B equals, work this out. You can actually substitute a plus b into this, which is very convenient. So b equals -4, and a is 6. So 6 over x minus 3 plus -4 x minus 2 equals 2x x squared minus 5x plus 6. So piecewise functions. So all the functions we had done have almost always have been continuous, as you say. There are always one rule. So x squared plus 3 is always x squared plus 3. I mean, piecewise functions may be continuous, but I'm using a vague sense of continuous. But continuous as a sort of, like, it follows only one rule. What a piecewise function does is it assigns multiple rules to different intervals. So let's denote it. So x plus 5, 2x squared minus 1, negative x over 2. So this happens when x is less than or greater to -3. This happens when, and we usually put an if here, so if this happens when -3, open x less than or equal to 2, and x is greater than 2. I wouldn't fuss about how many people are present. I'm fine with it either way. So let's take f1. So it follows this because it's in this range. So 2 times 1 minus 1 equals 1. However, if we took -4, that goes under there, and this is the 1. Now, if you were to take f -12 and then composite it by itself a few times, so f -12, then first off, -12 is less than -3, -7, then it becomes -2, which follows this now. So 2 times 2 squared minus 1, 7, and 7 is more than 2, -7 over half. This isn't really standing for anything, it's more of a exercise per se. Now I'll leave off with one last note before we end the lesson. But what we did just before is a piecewise function, because as this equals x1, x is more than 0, and -x if x is less than or equal to 0. But with that, that'll be it for today. So see you guys next time.